In this video, we're going to be talking about how to draw and label a heating and cooling curve for any substance. We are going to focus specifically on water, but it can be applied to anything. A couple vocabulary words that we need to review or teach, depending on what point in the year we're in and the order that this is taught in, but the individual phase changes. So now we know some of these words. We know when a solid like ice turns into a liquid, we call it melting. The scientific word is fusion. When a liquid turns into a solid, like water turning into ice, we call it freezing. The scientific word is solidification. When a liquid turns into a gas, we would normally call it boiling. The scientific word is vaporization. And when a gas turns back into a liquid, we would call that condensation. We actually use the scientific word for that. Like, for example, when you take a shower and you see the water starts to condense onto the mirror or glass around it, some people would call it fog, but the proper word is condensation. There are two others. Turns out you can, under special circumstances, skip the liquid phase in both directions. So a solid can turn directly into a gas, or a gas can turn directly into a solid. The words are, for a solid jumping to the gas phase, we call it sublimation. And when a gas turns back into a solid, skipping the liquid phase, we call it deposition. So you've definitely seen some of these. Deposition, the most common naturally occurring form of deposition would be frost. So in the fall, when it starts to get cold out at night and you walk out and you see essentially ice on the leaves, that was deposition. It didn't actually, on nights when it frosts, if you pay attention, you'll notice it doesn't rain that night. So the water had to come from somewhere, right? The water, a lot of people would think that the water might come from the grass blade or the plant itself. It turns out it doesn't. It comes from the air. And so the water is in the gas phase, and if the conditions are right, it will crystallize onto the blades of grass, and you see them in the morning as ice. They look like almost little snowflakes. And so that is deposition. Sublimation in the nature, I don't really know of any examples. There are some things that do sublimation, mainly dry ice, if you've ever seen that, or iodine, they can sublime, but we'll talk more about those in a different lesson. Some more vocab words. Entropy is disorder. So when we think about our three phases and you look at the three diagrams, which diagram is the most organized? Well, that would be the solid. So the solid would be the lowest entropy, because remember, entropy is disorder. And then the reverse, the gas, would be the most disorganized, and therefore it would have the highest entropy. Exo and endothermic, and then we can actually start labeling our graphs. So if we break the word up, exo and endo you've heard of in biology. If you think about an exoskeleton or an endoskeleton, we have endoskeletons because our skeletons are on the inside, and bugs have exoskeletons because their skeletons are on the outside. Well, the same use of the word is here, except now instead of skeleton, we're adding the word thermic, which refers to heat. So exothermic means heat is exiting the system. When you think of it, think of exo for exit, and then endo would be entering. So exo, exit is a little bit easier to remember. So for exothermic, heat is exiting the system, and for endothermic, heat is entering the system. All right, so those are exo and endothermic definitions. And then our next two, we just need to go over what chemical reactions look like. So the first thing you have to recognize is that chemical reactions are always separated by an arrow. So my arrow is right here. Everything on the left of the arrow is what we start with. It's what goes into the chemical reaction. We call it the reactants. Everything on the right side of the arrow is what we end with. It's what comes out. We call it a product. So when we think about reactants and products, these two chemical reactions are the chemistry way of saying something very simple. This one on the left is basically saying ice is melting, but it doesn't. When you look at it, it's obviously not as obvious. So this is H2O and this is H2O. The difference is this S means it's in the solid phase, so that's ice. This L means it's in the liquid phase, so that we call that water. And if you look, the energy or the heat is on the left side of the arrow, so it's going into the reaction. So what this is saying is if I take a block of ice and I add a specific amount of heat, I get liquid water. That's a very fancy way of saying you're melting an ice cube. The reverse is also true. If I take liquid water and I can turn it into solid water by removing the heat. Okay, so it's worded a little differently, but this is how we unfortunately have to read them. So liquid water turns into solid water if you pull out the heat that made it a liquid. So it's basically the reverse of that. And then the last thing we have to do before we draw our heating cooling curves is talk about kinetic and potential energies. So heating cooling curves look like this. They kind of look like steps going up and down. Don't worry about why they're different lengths. We'll get into that at like why this platform is shorter than this platform. We can get into that a little bit later. But here's the way to remember kinetic and potential. It's very simple. Kinetic energy, otherwise known as average kinetic energy, or AKE, is the temperature. So if we look at this graph, temperature is on the y, that means temperature is changing on the angle parts and it's staying the same on the flat parts. So if we're reading this from left to right, then the kinetic or the temperature goes up on these three angles and it goes down on the same three if we're looking at a cooling curve. Okay, so that's kinetic energy. Now the thing to remember is that when one form of energy is changing, the other remains constant. So if we think of it here, on the flat parts, the kinetic or the temperature is not changing, that's why it's flat. So therefore, if the kinetic is staying the same and we're still going to the right, then the potential must be increasing. And then the reverse is true here. So when kinetic is going up, potential is not. And when kinetic is staying constant, potential is increasing as we go left to right, or all decreasing as we go left to right for cooling. Now, what's the difference between kinetic and potential? Well, kinetic is obviously heat or the motion energy, whereas potential obviously is potential energy. Now, chemical potential is a little bit harder to explain. Everyone understands, like, for example, if someone was doing construction and they have this big heavy beam and they're lifting it up with a crane, you don't walk under it because obviously if it falls, it will crush you. That's physical potential energy. Chemical potential is a little bit less obvious. It has to do with the molecules and how far apart they are and what they're doing. And so we're just going to learn it as kinetic versus potential, and we're going to really define it as a kinetic or not kinetic. But potential is there. It is a little bit more complicated. We can explain it more if you need more than that at a later date.